So we are talking about series. What's a series? What is a series? Yeah, so you got a sequence, you got a list of numbers, and just adding them all up, right? You're adding them all up. And we're looking at different kinds of series and trying to figure out if when you add them all up, do you get a finite number? That's called the series converges. Or if you add them all up, it does something else, right? It adds up to infinity or negative infinity. Or it keeps bouncing around, okay? So that's called the series diverges. So we're learning these different tests about different kinds of series to understand those and analyze them. So a sequence, we said, is an ordered list. A series is the sum. So it's kind of like we're building a toolbox. We're going to come to any series, and we got to figure out which tool do we pull out of the toolbox to analyze it for whether it converges or diverges. So I want you to take 5 minutes with a partner and write a headline, just the headline for each of these. Like if you had to summarize it in a nutshell, what is the headline, or what, in a nutshell, what is each of these for analyzing series for whether they converge or diverge? So just take 5 minutes to go through each of these. Go. Everyone's got a partner. Everyone's talking to somebody. Don't flip through your notes. See if you can remember. Don't just flip through your notes and read your notes. See if you can remember. Okay, let's talk through these here quickly. The divergence test. Is it Nick? Are you Nick? Tell me about the divergence test, Nick.
So if it rises at a rapid rate with no sign of converging, it diverges.
Okay, what do we think? Agree with that, James? What's the divergence test? So it's more mathematical than that. Let's see. So what else here? Ray, what do you think? Divergence test. Yeah.
I think it is if the sequence is not convergent with zero, the series will be.
Yeah, he nailed it, right? So if the sequence, given a series, if the sequence doesn't converge to zero, so here we're saying the limit of the sequence doesn't go to zero, then the series diverges, right? This is the first thing we always check. In order for the series to have a chance to converge, that sequence has to go to zero, which makes sense if you're adding them all together, right? All right, geometric series. Steve, what do you think?
I said for a series that's in the form of AR I minus 1,
Uh-huh.
if R is greater than negative 1 and less than 4 and less than 1, then series will converge.
That's right. And the sum, we know for this one, we actually know what the sum will be. This is kind of the only one that we have that. All right, so converges when R is between negative 1 and 1, and the sum is A over 1 minus R. And last time we found an even stronger conclusion about this, right? What was the stronger conclusion we discovered about geometric series? If a geometric series converges, then also what? It's absolutely convergent, right? So it converges absolutely as well. As long as it converges absolutely, meaning it never needs alternating help to converge. Okay, P series. Zoe. Mm-hmm. Right, good. So it's diverges when P is less than or equal to 1, converges when P is greater than 1. Okay, comparison test. So the series diverges if if it's bigger than a known series that diverges, right? This is the headline. And it converges if it's smaller than a known convergence series, right? So if all the terms are larger than the terms of a series that diverges, it diverges. Or if all the terms are smaller than a series whose terms smaller than a series whose we know converges, then it converges. All right, and then last time we did the alternating series test. As long as the positive part of the series, we know it alternates, negative, positive, negative, positive. As long as the positive part decreases to 0, then it converges, right? So before, here's the key to this. Before, with the divergence test, we said that if the sequence goes to 0, that's required but not sufficient to say it converges. But now with the alternating series test, it is sufficient if it alternates, right? All the positive terms have to do is go to 0, decrease to 0, and that thing converges. Why? Because it gets this massive help by every other term being negative, right? And then we did the ratio test last time. So we looked at this thing, which was kind of like what? What is this ratio? We said is like what value that we talked about before? What's that? It's like R, right? It's like the multiplier you use to get from one term to the next, right? That's what geometric series does. You just keep multiplying by R over and over again. So this ratio is kind of like R. And so what we're seeing with the ratio test is, does this series kind of like become a geometric series? Does that multiplying ratio, does it have a limit that's less than 1? Then it's like becoming a geometric sequence, and then we know we'll have absolute convergence. Okay, any questions on these? Any questions? So knowing how to use each one to analyze is important, but then there's this other skill of, given any series, do you know which tool to pull out to use? And so you have a longer web work that's due Monday night, and we're going to be practice for that because they're kind of mixed together. Any questions? Okay, so let's do. So we did this example last time, and our conclusion at the end was we got that limit was equal to 3. Is that right? So when we did this example at the end of class last time, we said the limit was equal to 3, and so our conclusion was that this is like becoming a geometric, as you go way out in the terms, it's like becoming a geometric series with R value of 3, but it's also not only that, but then it's also alternating. Do you see this? So negative 3 to the j. See, that looks a lot, it's virtually geometric, right? Negative 3 to the j is a geometric. Now it's divided by j cubed, so it's not geometric, but we see that geometric portion there. And so what is this? It's like geometric series with R equals negative 3. So in reality, it's kind of like becoming a geometric series with R equals negative 3. Okay, but we're testing for absolute convergence, so we put the absolute value on there. All right, so let's do a new example. Okay, so what we said was we can always start now by writing this thing the first time as a to the I plus 1 times the reciprocal of a to the I. And that'll save us a step of a lot of writing. So what does that look like? So we're looking at the absolute value of negative 1 to the, so then we're looking at the I plus first term. So this is 7 I plus 1 squared. I plus 1 cubed plus 4. So that's a I plus 1. And then rather than writing this huge fraction with another fraction, we can just multiply by the reciprocal of ai, which is I cubed plus 4 over Negative 1 to the I. 7I squared. Okay, and so kind of when these get more complicated, what you want to do is you want to gather like things together in the numerator and denominator. Okay, so first of all, negative 1 to the I plus 1 over negative 1 to the I. What is that going to equal? Negative 1 where? Top or bottom? Top. You've got, listen, look, you got one more negative 1 multiplied in the top than you do the bottom. So that will leave just one negative 1 in the top. Okay, and then we're going to gather like stuff together here. 7I plus 1 squared. And the 7I squared. So those are alike. So we're going to gather those together. And then we're going to gather these together. I cubed plus 4. And I plus 1 cubed plus 4. Okay, any questions so far? Have I done everything correctly? Okay, so now we have to remember our sequences, right? We spent the whole first week in this unit learning how to analyze sequences for convergence or divergence. So we have to do that with this one. So we look at this. As I gets big, what does this become? So this is rational function, right? Leading term here is 7I squared. Leading term here is 7I squared. Therefore, 1, right? Leading term here, I cubed. Leading term here, I cubed. Limit, 1. So therefore, I can go right to it here. As I gets big, what does this whole thing do? Goes to 1. As I gets big. Absolute value, right? Absolute value.
That makes a lot of sense.
Absolute value. Yes, negative 1 inside, but absolute value is 1, right? Conclusion? So the ratio test yields no conclusion. It means we have to try something else. So we look at this and we go back to the toolbox. Say, what can we pull out of our toolbox that might help us here? Geometric series, P series, comparison test, alternating series test. Anything apply? Yes, one of those applies. Which one? Is it geometric? No. Is it a P series? No. Comparison to P series? Maybe. Is it an alternating series?
It is.
Alternating series, right? Alternating series. Does the positive part of this series, 7I squared IQ plus 1, decrease to 0? That's the requirement to apply the alternating series test. Does 7I squared over IQ plus 4, does that decrease to 0? Yeah, because well, look, you've got 7I squared and I cubed, right? That limit is the limit of that is 0. Therefore, it meets the requirements. So by the alternating series test, the series converges, diverges, converges. Now, question, does it converge absolutely or is it conditionally convergent, right? So, is it absolutely convergent? Well, what would we look at? We look at the sum of 7i squared over I cubed plus 4. And we ask the question, does that converge? If that converges, then this converges absolutely. It doesn't need the alternating help. If this diverges, then it's conditionally convergent, meaning it needs the alternating help. 7i squared over I cubed plus 4. Does it converge or not? Why diverge? Because this thing goes to, as I gets very large, 7 over I. Right, so this is kind of like 7, it kind of is like 7 times the harmonic series. You see that? So as I... So therefore, without the alternating help, we have basically, in the long run, it's like 7 over 7 times the harmonic series, which diverges. Conclusion about the original series? Conditionally convergent. Did you follow all that? So ratio test yielded a limit of 1, which means no conclusion. We saw the alternating series test applied. By the alternating series test, it converges and meets the requirements, and so it converges. But then we went further and said, does it converge absolutely or not? So to look at absolute convergence, we take all the positive, the series has all positive, basically the absolute value of this. Showed that that was essentially the harmonic series, which diverges. So conclusion is that the series is conditionally convergent. It needs that -1 to the I to converge. Okay, any questions? Okay, can I erase? Okay, you try one. All right, tell me. Okay, good. Keep going, you're doing good. Okay. And what is -1 to the k plus 1 over -1 to the k? It's -1. Okay, keep going. So what can you make sense of those there? Two. This is 1. Okay, agree with that? K factorial over k plus 1 factorial. So what does that become? 1 over k plus 1. Remember? So k factorial. So k plus 1 factorial equals what? K plus 1 factorial equals k plus 1 times k, k minus 1, k minus 2, etc. But notice what that is. K plus 1 times k factorial. Every factorial has all the lower factorials as factors, right? You've got every factorial that's a lower one as a factor, including in this one k factorial. So that k factorial will cancel out with that k factorial, and all you have is 1 over k plus 1. Okay? As k gets big, what do we have? Super easy, right? Super easy sequence to analyze. What is it? Goes to? 0. As k gets big. Conclusion? Therefore, the series what? Converges absolutely. Because 0 is less than 1. So what is this series like? It's becoming like what? This series becomes like a geometric series with r equal to? R equal to? Remember, this ratio is like r. This is like r. It's just instead of being constant, it's changing. Therefore, this is becoming like a geometric series with r equals 0. Right? So we analyze, we simplify that thing. We simplified it. And we say as k gets big, that's going to 0. So this ratio is going to 0. So the multiplier is going to 0. That's like a geometric series with r essentially in the long run becoming 0. That's definitely going to converge, right? Questions on that one? And what does the convergence absolutely mean? Whether or not it alternates or not. So this is an alternating series. Doesn't have to alternate. This one will converge, whether it alternates or not. Any questions?
So if it will be 1 to the k times 2 to the k, it will still converge to 0, right?
Right. If you just had 2 to the k over k factor, the series doesn't converge to 0. The series converges to a finite number. Right? But the multiplier is converging to 0. So yeah, without the minus 1 to the k, this thing still converges. Therefore, converges absolutely. Okay, write this down. Okay, check what I did for the first step. Is it right? Is it right? Gray thinks there's something wrong.
It should be 3 times. So on the denominator, it's 5 to the third power parentheses times k plus 1.
I need parentheses here, right? It makes a difference, right? I need parentheses here. So it's not 3k then plus 1, it's 3 times k plus 1. And maybe in this problem it doesn't make a difference, but in future problems it might. So you got that's 3 times k plus 1. And that's important. Okay, so how many negative 1s do we have? 1 negative 1 on the top, right? All right, then what do I have? K plus 2 factorial over k plus 1 factorial equals? Just k plus 2, right? 5 to the 3k. So what is this really? This is really 5 to the 3k plus 3, not plus 1, right? Because it's 3 times quantity k plus 1. So I got 5 to the 3k and 5 to the 3k plus 3 together makes? How many more 5s do we have multiplied in the denominator than the numerator? 3, so it's 5 cubed more. There's 3 more 5s multiplied in the denominator than the numerator. This is supposed to be an exponent. Okay, so what from here now? He says this sequence goes to infinity, therefore the series diverges. Agree? So rather than 3 dots in a triangle like this, that means therefore, right? Therefore. So the multiplier, right? The multiplier from one term to the next is doing what? So this multiplier is doing what? This is what we multiply by one term to get the next term. And in the long run, what does that do? What does this do in the long run? It goes to infinity, right? The multiplier goes to infinity. So there's no way, no chance this thing could ever converge if you're adding all those things up and you keep multiplying by a number that's getting infinitely large. Okay, questions on this one? Okay, one more.
Yeah, you're overthinking it. Yeah, no problem. It's just J plus 2. The problem is I don't understand this part right here. Right. Right. Oh, good point. Good point. Yeah. Right. I was. I'd say. Because 6 squared. This is 3 times 3 squared. Because at the bottom, remember? So you see how you have 3, 2j. The other one should be 3, 2j plus, or 3, 2j plus 2. And so you should have a remainder of 3 squared.
Oh.
And so then, yeah, you should have 6 squared at the top, 3 squared on the bottom. And you should get a 4. I got that. That's good.
Okay, you can check. I put my solution. This is my final thing that I got to. -1, 4j plus 2 cubed in the numerator, 4j minus 2 cubed, denominator, and then 6 to the j plus 2 over 6 to the j plus 1 is 6. And then here's where you have to get this right, or you're going to make the wrong conclusion in the end. So it's 3 to the 2 times quantity j plus 1, which ends up being 1 over 9, not 1 over 3. Therefore, that goes to, this whole thing goes to 2/3 as j gets big. Conclusion? This converges absolutely. This converges absolutely. In essence, what can you say about this series in essence? No? What can you say about this series in essence? Okay, it's absolute convergence. But what did this tell us? What did this process tell us about this series? What's it? Good. So it's in the long run, it becomes like a geometric series with r equal to 2/3, right? This ratio, this limit that we found, is like what r, it's becoming like r.